Let's get started with our simulation here. What I'll do is we'll design the inverter, a single phase inverter from scratch. Okay, there are many ways to design single phase inverters, but today I'll show you how we can design this inverter using like H-bridge inverter for only 4 switches with RL load. Okay, and also we'll see how to implement the pulse width modulated signal from scratch. Okay, we'll not use the PWM blocks that are already there in the libraries. We'll make our own ones, our own recipe. Okay, so here you can find that we have the library browser. You can find the passive components here. You can select resistor and inductor because we need this one for the load. You can go to power semiconductors and select IGBT with diode because we need to make sure that we have anti-parallel diodes to allow the current. Since we have RL load, we expect that the current is not in phase with the voltage. So for sure we need IGBT with diode. Okay, and also we need a DC power supply at the input. So here we can go to power supplies or sources and select voltage source, not control, just a DC power supply. Okay, what else we need is we will need some meters here, voltmeter and ammeter, to measure the voltage and the current. And also we need to go to system here and pick the scope. We need a scope to see the output. We need display to measure some like measurements like the total harmonic distortion. Here you'll find that there is a ready block is called total harmonic distortions. Of course you can search the blocks here, but I like to just navigate here and try to see where you can find these ones. Also we can find the signals from and signals to this in order to just make our design or our diagram here very nice without a lot of wires, connections. Let's go to control here. We need a sine wave and a triangular wave because we need to design our own PWM, right? So we need to compare the sine wave with the triangular wave. Okay, so we need these two blocks. Also we need go to math here. What we need from here is nothing. Okay, logic, relational operators to compare, and also we need logical operator to make sure that we can use not like the signal and it's it's complementary, like 1 and 0. Keep these blocks here first, not need them now. So let's define our input voltage to be 100 volt, for example. Okay, for simplicity I'll remove the names from all the blocks. Okay, here I'll duplicate this one, control drag, then duplicated, control drag, duplicated. Yeah, magic. Okay, so we connect this one here at the input, all collectors here together on the upper, and emitters together on the lower side, right? And these the first leg is connected together, switch 1 and 4, let's say, and these are connected together. Okay, I'll also remove the names from here. Okay, connect the RL load together. I'll put this inductor to be 10 millihenry, and this resistor to be 1 ohms only. So try to make a heavy inductive load here. And of course the output is connected between the first leg and the second leg. Okay. Okay, now we can connect the voltmeter on the output here. Okay, and connect the ammeter here on the output as well to measure the output voltage and current. So what we need to do actually is to measure the voltage and the current on the output, and compare this voltage and current with, let's say, with many modulation techniques. Like, let's see the difference between this modulation technique, the unipolar and the bipolar. Okay, let's go here and pick the multiplexer, let's say, because I want to put the voltage and current at one scope. Okay, and we need the total harmonic distortion block to measure the total harmonic distortion on the current. Okay, total harmonic distortion, they put it in the filter. Very good, no problems. I'll put it here, and I measure it for the current. Okay, let's highlight all these. We know all these blocks, so delete the name. Okay, very good. So now we have the inverter, the output are a load, 4 switches, right? What else? Okay, now we need to send signals to these 4 switches. Okay, so what I'll use is the tag here. Okay, let's say that we have, I'll say that this is switch A. Okay, we said that switch A and like switch 1 and 4 work together, so I'll send the same signal to these switches. Okay, so I'll just send SA and SA here, same signal, and switch B here, for example, here, this I'll change it to B. Okay, and first we'll examine the bipolar. So we'll compare a sine wave with a triangular wave, and send the signal here, switch A, and the opposite will send it to switch B, simply like that. Okay, so here's switch A, and here we have switch B. Okay, so what we'll do here actually is taking this triangular wave and the sine wave, how much the, okay, let's define the triangular wave. Now I'll compare the sine wave with the triangular wave. So we need to make sure that the triangular wave and the sine wave like in the same range. So if we select the sine wave from -1 to 1, the triangular wave must be also from -1 to 1. Okay, if the sine wave from -0.5 to 0.5, the triangular wave should be also from -0.5 to 0.5. So our sine wave from -1 to 1, the amplitude is 1, so I'll change this one to -1 to 1. Okay, the minimum value is -1, the maximum value is 1. Okay, The frequency here, I'll select only 1 kilohertz carrier frequency. Okay, so the higher frequency, like the sine wave is 50 hertz, but the carrier wave is 1 kilohertz. Okay, so I'll say that this is 1E3. Okay, and delay, no delay, so I'll keep this one like that. You can put this one on the scope to see if this is what you need or not. Okay, so always put this one and test it on the scope. Okay, now the sine wave here, the amplitude, you can keep the amplitude to be 1. I'll put it 0.9. When you put it 0.9, which means the modulation index is 0.9, right? Because this is compared to the triangular wave, which is 1, this makes a 0.9 modulation index. No bias. I will not shift this sine wave to any value. The frequency, I'll keep it to 50 hertz. So we can go here and select hertz and degrees. So I'll put this one 50 hertz. Okay, and the phase is 0. Very good. Now I'll compare these two values. So I'll say if the triangular wave is greater than or equal the sine wave, then send 1. If not, send 0. And this will be not. Okay, so here again. So this will be sent to switch A, and the not will be sent to switch B. Okay, simply like that. Now let's see the sine wave, the triangular wave and the sine wave before making the simulation. So I'll measure the triangular wave and the sine wave here and say start. Okay, so what we need to do actually is just make sure that, look at this here, the frequency is like the range of the simulation is too large. So what I'll do is to reduce this one to 0.06. Okay, apply and run again. Okay, so here we have a sine wave with amplitude of 0.9, and this is compared to a triangular wave, right, with amplitude of 1, right, with modulation is 1. Very good. Now let's see these values here. Switch A, for example, how it looks like. Okay, so this is the expected waveform. Okay, so let's see the output waveform here. Okay, very good. Now you'll find that this is exactly what we expect. We have a bipolar output. So the red one is the voltage waveform, okay? But the green one here is the current waveform, okay? You'll find that the current waveform is distorted, is not a pure sine wave. You see here we have some distortion when the amplitude is increased. Okay, let's see the total harmonic distortion, how much. Here we have to make sure that you select the right fundamental frequency. So here our frequency is 50 hertz because we define it in the modulation. So, and sample time, I'll put like maybe 1e-5 or something, or keep it 0, it's up to you. Simulate again. You'll find that the total harmonic distortion is 0.05 in this case. Okay, so this is a simple modulation technique. It's a bipolar modulation, right? Try to decrease the frequency here. Instead of 1 kilohertz, just put it, for example, 700, and see the output. You see now the total harmonic distortion is increased, and you can clearly say the distortion here, and the pulse width or the frequency now is decreased, so the PWM waveform like clearly appears, right? Okay, very good. Now what we need to do actually is to duplicate this design and make a unipolar modulation. Okay, what I'll do here actually is just duplicate the same. Okay, just let me get rid of these ones. Names, okay. Now of course you can go here on Plex or Simulink. You will find that we have in control, like for modulation, like you can for pulse width modulated waveforms. Here is the modulators. You'll find like symmetrical PWM, sawtooth PWM, three level. So you'll find a wide range of pulse width modulated blocks. Okay, but the problem of these blocks is just you can just use them here in simulation. You'll not be able. It's better for me. I like to design the PWM from scratch. Why? Because when you go to DSP or microcontroller, you can design your own PWM. Okay, but now we know exactly what to do if you want to design your own inverter, right? We know how to compare these things. We can compare. We can write our own program and design our inverter, right? No problems. Now I'll duplicate this one. So this one is we said the bipolar one, and here just control drag, you'll get the other one. Okay, the difference only in the modulation technique. Again, we need a sine wave and a triangular wave here. So we said for the unipolar, we need to generate two sine wave, the sine wave and negative sine wave, or we can shift it by 180 degrees. Okay, and compare these two sine waves with the same triangular wave. Okay, so what we need to do is here we can say that the amplitude is 0.9, the frequency is 50. We can simply generate two sine waves here by changing the phase here. We can say the phase is 0 and 180 degrees. Okay, so by this way I generated two sine waves, the same identical one, but the first one without phase shift, the other one was with 180 degrees phase shift. Okay, so that's it. Now we can use the comparator again here. Compare this triangular wave with the first sine wave. Okay, so also we can use a demultiplexer to extract these two sine waves. Okay, so this wire here has two signals. The first one is a sine wave, the other one is the opposite sine wave or the shifted sine wave. So first one we compare this the non-shifted sine wave with the triangular wave, and then we compare the other sine wave with the triangular wave. Okay, so what we can do here actually is to again here compare this triangular wave with the second sine wave. Now let's copy these ones here. Now I'll send this one to switch 1. So this is switch 1. Okay, and the negative or the not one, the complementary one to switch 4. Now again here switch 1, then 3 and 2 here, so we can duplicate this one and send this to switch 3. Where is switch 3? It's here. This is switch 3, and this is to switch 2, and switch 2 is here. Note now this now here we said for the bipolar we just send switch A and switch B, 2 signals, that's it, and these are same, identical, and these are the opposite. Now for the unipolar, each leg receive different waveform, okay, different signal. Switch 1 receive different signal than switch 2 and 3, but switch 4 is the complementary to switch 1. When switch 1 is on, switch 4 is off, and so on. Okay, same thing for switch 3 and 2. When switch 1 3, switch 2 is on, so switch 2 is on. Same thing for the legs, so these are same. But here switch 1 and switch 2 do not receive the same waveform. Okay, now the first one we compare it with the sine wave. The other one, the other leg, we compare it with the minus sine wave. Okay, so now okay, all these sent like this. Hopefully everything is okay now. Let's try to make the simulation. Start. Okay, let me plot these here. So before seeing I'll try to see the sine wave. We need this one as well. So here we have 2 signals, and this here we have 1 signal only. So okay, we can remove this one and make this on 3. Okay, and connect after the, hopefully now it works. Okay, look at this one. That is exactly what we are looking for, right? We have sine wave, okay, compared with the triangular wave, and this is sent to the first leg, and the other one is a shifted sine wave by 180 degrees, or the negative sine wave, minus sine wave, and this is compared with the same triangular wave and sent to the second leg. Okay, now let's look at the output here. You'll find that the output looks like that. It's a unipolar output, right? Like the output is a voltage is changing from 0 to V maximum to 0, 0, V maximum 0, and so on and so forth. It will never jump from minus V maximum to plus V maximum, right? And also you can see the waveform here. The sine wave has much smaller ripple or much smaller distortion than the previous one, right? Like if you try to compare this waveform with this one, look at this waveform, the current one, okay, and this one, the output here, this is very distorted, and the other one is like it's perfect. Now if you compare these 2 waveforms, you will find that we use same conditions, same switching frequency, same carrier frequency, everything same, okay? But here you'll find that for the unipolar, the output waveform is much smoother than the output waveform, the current waveform on the input, right? On the bipolar modulation or bipolar waveform. Okay, look at the total harmonic distortion for this one. You'll find that the total harmonic distortion for the bipolar is 0.07, but for the unipolar is 0.01 or 0.02, which is significantly smaller than the bipolar one. Okay, now try to increase the frequency, make it 1000, 1K, and here 1K, for example. Okay, when we increase the frequency, the switching frequency, you find that the total harmonic distortion becomes smaller for both. So here it becomes 0.05 and here 0.014. Okay, and for the waveforms, you can see the difference as well here. So here the output is much smoother than the previous one, and the switching frequency is higher as well. Okay. Now what I need to do actually is to try to I'll show you how to make the dead band on MATLAB on Plex or on MATLAB Simulink. Of course, you can use the same blocks, by the way, here on MATLAB. It's up to you. Okay. How can we implement the what we call the dead band here? I'll go for this modulation technique. Now for the dead band, you cannot say that you cannot use this operator and say if it's larger than or if it's greater than this value, then send 1 and use not. When you use not, this will make the transition exactly same. Okay, so what we need to do is to make comparison. Now I'll shift the sine wave to be shifted up by a very small value and compare it to the triangular wave, and this will make sure that we have a wider range of PWM, like the pulse width will be wider at some point, and then we can generate what we call the dead band. Okay, so now what we need to do actually is to copy this one here. We can compare this triangular wave with the sine wave, but here I'll remove the knot from here. I'll copy this one again here. So what I'll do actually is I'll compare this triangular wave with a sine wave, but this sine wave, it will be like shifted up or down by a very small value. Let's say it's 0.05. Okay, and this sine wave, it will be shifted by minus 0.05. So when you compare the sine wave with the triangular wave, and the sine wave is shifted up or down, this will make sure that the pulse width will be either wider or smaller. Okay, so what we can do actually here is to compare this one here. See it on the output here on the scope. I'll select 2 plots. I'll compare first the triangular wave with the sine wave, okay, and see if the triangular wave is larger than this shifted sine wave, I'll send it to switch 1, okay. If the triangular wave is larger than the sine wave that's shifted down, I'll send it to the other leg, okay, but this one must be smaller than here. So again, if the triangular wave is larger than the sine wave that is shifted up, so send it to switch 1. If the triangular wave is smaller than the sine wave that is shifted down, send it to switch 4. Okay? Now we'll make sure that we have a small dead band between the complementary values. Okay? So again here, I'll send this one here and this one here similarly, and see. Okay, now this is a unipolar design. Okay, let's see the simulation here. Look at this waveform. Now let's examine the dead band. Now if you look from far away, you'll not notice anything, but if you try to make sure that we have, if you zoom this one here, look at this one. Now this becomes 0 first, then this, after this become completely 0, this will jump to the 1, right? Look at this one here. This is the dead band from this time to this time. This is the dead band. Of course, this is a very large value, but you can change it to 0.01, for example. Okay, it depends on your switches. If your switch is like very fast, you need a very small dead band. If your switch is slow, you need a larger dead band. So this by experiment. You need to experiment your switch and see how much the dead band that you require. Okay, look at this one here. this waveform becomes 0 first, and then after completely becomes 0, this jumps to 1. Okay, and so on here. If you want to see these values, same thing. This is the dead band here. This becomes 0 first, then after this becomes 1. Okay, and so on and so forth. Now same thing happens here for the other leg. Here again, this becomes 0 first, then this jumps to 1. Now, for the previous modulation, you'll find that this becomes 0 at the same time this jumps to 1. Okay, this is okay for you'll find that this is 0 like that, and this line is here, right? This is okay for simulation, but for hardware, this doesn't work. Okay, you need to make sure that you have a dead band to make sure that your switches are not damaged. Okay, do you have any questions so far for this one? Okay, if you don't have any question, I'll stop here for today, and I hope that you enjoyed this lecture. Maybe you find something useful. If you have any question, just send me an email, and I'll see you next week.